Okay, so we're looking at question 1834, single-threaded CPU. You're given n tasks labeled from 0 to n minus 1, represented by a 2D or integer array tasks, where task set I is equal to n queue time and processing time, which means that the ith task will be available to process at n queue time and will take processing time to finish processing. You have a single-threaded CPU that you can process at most one task at a time, and will act in the following way. If the CPU is idle and there are no available tasks to process, the CPU remains idle. If the CPU is idle and there are available tasks, the CPU will choose the one with the shortest processing time. If multiple tasks have the same shortest processing time, it will choose the task with the smallest index. Once a task is started, the CPU will process the entire task without stopping. The CPU can finish a task, then start a new one instantly. Return the order in which the CPU will process the tasks. Okay, so looking at example 1, we see that tasks is given to us with 4 different values inside of it. The output is 0, 2, 3, and 1. The event goes as follows. At time is equal to 1, tasks at 0 is available to process. Available task is now 0, right? Also at time is equal to 1, the idle CPU starts processing tasks at 0. Available tasks is now nothing, right? Because we want to make sure that when the n queue time is equal to a specific time, then only we can add it to the available tasks. In our case, time is equal to 1, and so n queue time for this is 1, and so we can add it to the available tasks. And since the CPU is idle, we're able to start looking and processing the 0th task. Now, at time is equal to 2, task 1 is available to process, right? Available task is now 1. The task 1, which is this, is available to process because the 2 is equal to the time 2. So now available task is 1. At time is equal to 3, task 2 is available to process, so that's this. Available task is now 1 and 2. Also at time 3, the CPU finishes task 1, and starts processing task 2, as it is the shortest. Available task is equal to 1. So what happens here is that 2 and 4 and 3 and 2 got added into this available tasks here. Now 3, even though the index is bigger for the NQ time, is bigger than the one previously, the processing time is smaller. So the processing time is 2 for this and 4 for this. So it processes the one that has 2 before it does the 4. So at time t equals to 4, tasks at 3 is available to process. Available task is at 1 and 3. Okay. At time is equal to 5, the CPU finishes task 2 and starts processing task 3 as it is the shortest. The available tasks is equal to 1. So again, when it gets to time 5, this task was done processing. But now the processing for this item is smaller than the processing of this item. So we process this before we process this again. So at time is equal to 6, the CPU finishes task 3 and starts processing task 1. Available task is nothing. At time t equals to 10, the CPU finishes task 1 and becomes idle. Okay, that makes sense. Just running through the next example, tasks is equal to this list right here. Output is 4, 3, 2, 0, and 1. The events go as follows. At time is equal to 7, all the tasks become available. Available tasks is equal to 0, 1, 2, 3, and 4. Right, because at t is equal to 7, all of these NQ times are the same. Also at time is equal to 7, the idle CPU starts processing task 4. That's because it has the shortest processing time, which is 2. At time t equals to 9, the CPU finishes task 4 and starts processing task 3. Now available tasks is these 3 items. At time 13, the CPU finishes task 3 and starts processing task 2, because that was the shortest after that. Time 18, the CPU finishes task 2 and starts processing task 0. Available tasks is equal to 1. At time is equal to 28, the CPU finishes task 0 and starts processing task 1. Task 1 is right here, and that's and then our available tasks is equal to nothing. At time is equal to 40, the CPU finishes task 1 and becomes idle. Okay, let's go into the explanation for this problem and then start coding the solution. Okay, let's go over the explanation for this question then. So we're given the list tasks with 4 different values in it. Task at index 0 is 1 and 2. Task at index 1 is 2 and 4. Tasks at index 2 is 3 and 2. And tasks at index 3 is 4 and 1. Now, a good way to solve this problem is to append to the existing list the index that they're currently at. So, for instance, at tasks at index 0, we want to append to this part another value, which is going to be the index that it's currently on. We do that for every value. So for this one, tasks at index 0 is going to have the value 1, 2, and 0. At index 1 is going to have 2, 4, and 1. The next one's going to have 3, 2, and 2, 4, 1, and 3. We're doing this because it requires that we return a result with the index of the task, and we are going to be sorting this list, and because we sort it, it's possible that these values can get jumbled up. So we want to make sure that we save the index of them and then eventually return or pull that index value and then put it into a result that we're looking for. So we'll be adding that index into this tasks list, and we'll also be sorting it like I just mentioned. So the next item here is the updated list. The updated list is the tasks list, but it has the index value in it, and it's also sorted. It doesn't seem any different from this, but in an event that the indexes, the first value on each index was different, it would have been sorted according to that. In our case, it's already in an ascending order, so there's no need to sort. So after that, I have a bunch of different variables I've created. I have 2 different variables, I, which is equal to 0, time, which is equal to 1. I is the current index you're looking at in in tasks. So we're going to start off with 0, and then eventually we'll be starting off to look at the first task here, second task, third task, and fourth task. We want to run a loop where when I is less than the length of tasks, we run this loop, and in an event that it's greater than or equal, greater than or equal to the length of the tasks, so 4, we want to break out of this loop. Time is actually mapped to the first value on the first index in tasks. So tasks at index 0 and value 0, which is going to be the enqueuing time, and that's going to be the 1. So I'm going to initialize it with 1 off the bat. I also have 2 different lists, min heap and result. Min heap is going to be putting all the values that are currently being queued and in the process of being processed. Now, min heap is going to make sure that the smallest value is going to stay in the front, and we want to make sure, as the question requires, the task with the smallest processing time is the one that gets processed first. And so we want to make sure that when the min heap, we're putting it in a min heap because when we do push a value into the min heap, it's going to sort it based off the processing time that we have stated. The result is going to be the index values that we want to result for this problem, as it's going to be the 0, 1, 2, or 3, but in any different order based on whichever one gets solved or processed first. Okay, so the first thing that happens here is I check if a time value here, so 1, is equal to or greater than the time value for the ith index. So the time value for the ith index in tasks is 1. So time is greater than or equal to 1, and because it is true, we want to push the processing time and the index value as a list inside of our min heap, sorry. So because time is greater than or equal to the time for the ith index, so 0th index, which is 1, then we put the processing time and the index into the min heap. In our case, we get 2 and 0. Now, we also increment the I value because now anytime you want to look at the next value, anytime you want to look at a value, you want to look at the one after it. So in an event that the time here was greater than or equal to 2, we want to make sure that it's viewing this position, not the first one cell. So we increment our I by 1. Now, since the time is equal to 1, it's not greater than or equal to 2. And so because of that, we don't put anything else into the min heap. Now, since we don't do that, we just move on, and then we check if something is inside of min heap. In our case, we do have something inside of min heap. So we pop the first value inside of min heap, and this is the first index of the first value in min heap is the processing time. So we add to time the processing time, and inside of result, we append the index. So we pop this value, add or increment our time value by 2 because that's the processing time. That's how much time it took to process this specific job. And then the result, because this has already been processed now, so the result gets added, this value index gets added into the result. So that happens here. New time is 3, result is equal to 0. Now we repeat this process over again. Now we check if tasks at I, which is 1, if time is greater than or equal to 3 for that specific task. So for this, time is greater than or equal to 3. Time is greater than or equal to the value inside of tasks. So we know that that is true. So we want to put in the processing time and the index into our min heap. And that happens right here. I mentioned that we also increment our I because we want to move on to the next value and view the next value. So that happens right there. And now we check if the time, which is 3, is greater than or equal to time at ith index. So ith index is 2, and the value here is 3. So 3 is equal to 3, and it's greater than or equal to, so it's equal. And so we know that 2 and 2 also get appended inside of min heap. Now when you push this value 2 and 2 into the min heap, you should know that we sort it based off of the smallest value in the front. So in our case, it's actually going to be 2, 2 in the 0th index, and then 4, 1 gets pushed off. That's because the first index is what we're looking at. The first index in our case is smaller than the first index of the next value in the min heap. So because of that, it gets sorted based off of it, and the first value now is 2 and 2. Now, so once we add it into the min heap, we want to increment the I value, and we notice that I at 3, the time, which is equal to 3, is not greater than or equal to time for the index of 3. So there's nothing you need to do here, and move on. Now you check if min heap has a value, which it does, and so you pop the 2 and 2. The processing time here is the first index at 2, and we append that into time, and the second value, the index, gets put into result. So that item job also got processed. Now the next thing to do is to repeat this process. Our time got incremented to 5, so we repeat the process and we look at index 3. Time is equal to 5. So index 3, time has to be greater than or equal to the time in here, which is 4, NQ time, and that is true. So 1 and 3 get put into the min heap. Now like before, the 1 is smaller than the 4, and because we're sorting it by the first index, it's going to be ahead of the 4 and 1. So we push it into the min heap, and we want to increment our I value. Now there's nothing else you can do, there's no other value here, so we want to move on and check if there's a value inside a min heap. It's true, we do have a value inside a min heap, so we pop the value. To our time, we append the processing time, which is 1, and to our result, we append the 3, the index, and that's what happens there. Now we repeat the same process again, and we go through this loop again. Here now, I is equal to 4, and as we checked, when I is equal to 4, it's greater than the length of the tasks, so we want to move on. There's nothing we need to check here. Min heap still has something, so we need to pop that value. So we pop the 4 and 1, and the 4 is the processing time, so that gets added onto our time. So time will become 10, and the index 1 is going to get put into result. Now we repeat the same process again, and we notice that I is equal to 4, so we don't check any value inside of tasks, or we don't put anything into the min heap. And then we check min heap and see if there's a value inside of min heap. In our case, there's nothing inside of min heap, and so that's it. We return the result, and that's the answer we were looking for. Okay, let's go into the programming for this problem. Okay, let's go into the solution for this problem. I mentioned that we will be getting the index for every value in tasks and then appending it to tasks. So in order to do this, we're going to loop through the tasks, and we're going to do something like enumerate for tasks. So this is just getting the index and the value, and all we're going to do is go value.append and then index, right? So for the value inside of tasks, it's just going to append my index to it. Next, I mentioned that we want to sort our tasks list. So we can do something like tasks.sort, and you could just pass that, well, you could just do this, but it's better that you sort it by a specific item, just in case we didn't sort it by the 0th index when we were sorting it by the 1st index. You can specify by just saying key equals lambda x, and then pass what you want to sort it by. In our case, we want to sort it by the 0th index. I also mentioned that we have 4 different variables we are creating. One is I, which is equal to 0. Another is time, which is equal to tasks at 0, 0. That is essentially the first value inside of tasks and the first index, or 0th index of that. Right, it's a 0th value of tasks and a 0th index. Right, so that's a 1. I also mentioned that we need a result list and we need a min heap. Now, I will be doing a while loop on this, and while there's something inside of min heap, or my ith value is less than the length of the tasks. Now, there's a reason why I'm doing or. That's because I can be greater than the length of the tasks, as we saw in the example or the explanation I was giving before. So even if I is greater than the length of tasks, we want to make sure that if there's something in min heap, we want to pop it out and append that to the results when we do that. If we don't do this, the results is not going to be complete and it's going to return the wrong answer. So we're going to do a while loop while min heap, there's something in min heap, or our I value is less than the length of tasks. Okay, so if that is true, then there are 2 things I need to do. One is I need to check if my time is greater than or equal to the value in tasks at the ith index at the 0th value, right? So let's do that. So while time is greater than or equal to tasks at the ith index at the 0th value. So ith index could be any of these at the 0th value, which is 3, 2, 4, or 1, right? But we also want to make sure that I is less than the length of the task. So while I is less than the length of tasks, otherwise there's no reason to be checking this because there's nothing inside of tasks, right? My answer just gonna break. So yeah, so if that is true, then we want to make sure that we append that specific tasks value from 1 and 2 into the min heap. The 1 and 2 being the processing time and the index into the min heap. So you're just going to do that by doing heap queue.heap push, and then what list do you want to push it into, which is a min heap, and what values you want to push it into. So that would be tasks at I at 1 and tasks at I at 2. Right? So we're going to push those values in there. And we also said that we want to increment our I by 1. So we want to move on to the next value now. Now, in an event that this comes up as false, we want to then move on. And the next thing we want to do is check if something is inside a min heap. So we just simply do that by just checking if not min heap. This means that if there's nothing inside a min heap, and if there is something inside a min heap, if there is something inside a min heap, we want to retrieve the processing time in the index from the min heap, and we want to append the processing time to our time, and append the result or the index to a result. So we can get that by doing proc time index is equal to heapq dot heap pop, and then pass the list that you want to pop it from. In our case, min heap. Now we also want to append to our time the proc time, which is the processing time that it took, and we also want to append to our list the index. Now up here, what happens when there's nothing inside a min heap? Well, if there's nothing inside a min heap, the time will always keep repeating over and over and over again, and it's not going to break, and so it's just going to keep running in an infinite loop. In order to fix that, something we can do is just increment the time value by the next value in the tasks. So we can set the new time value to be equal to the tasks at I now. That way we don't have to wait on us to come to the next value, or like wait a long time until time gets incremented some way. We can just do time is equal to tasks at I and 0. So for questions like the one down here, we don't want to keep waiting for the next time to come over in an event that nothing got put into the min heap. So all we have to do then is just increment it by the time for the next value. And that way when you go back to the loop, there's always going to be that one item that gets placed into the min heap, because that time is always going to match. And so that new item gets put into the min heap, and then we do this this else part, and then the new proc time is going to increase the time value again. Right? Now, this is pretty much it. Now, at the end of this, we just want to return our result that we had created. And that's it. That's the end of the solution. Let's just run this code. Right, and let's submit this solution. Right, so just to help give the time complexity for this problem, it's going to be an n log n time complexity. This is because we are sorting here, but we're also using a min heap, right? Aside from that, it would have been O of n because we're just going through this specific list once, but because we're sorting and we're using a min heap, which also sorts, we have to do an n log n, and that's going to be our time complexity for this problem.